different from the previous attempts. And finally, I want to go over how our device performed when we tested it with users, and reflect broadly on the future directions of this type of technology. Navigation is an enormous challenge for blind and visually impaired people. So about 1 in 27 adults in the world have a vision impairment, about 250 to 300 million people, which I think is a number much larger than most people would expect. About 90 million of those people are severely visually impaired or totally blind, and 50 million people are totally blind. So there's a wide range of different levels of vision impairment. It's not one uniform thing. But regardless, navigation is a challenge for many of this group of people. I was surprised myself to learn that 50% of blind people never make independent journeys. They never leave their home by themselves. And 40% of people with some level of vision impairment rarely travel by themselves. And this is, of course, much lower than the rate of travel for the general population. And it has to do with the things that are difficult about navigation. Some of the impacts this has is, in the domain of employment, for example, about 44% of blind people are employed, which, a lot of people are making great efforts to try to improve. But being able to get from point A to point B, being able to navigate independently, to leave your home and, for example, go to your place of employment is a major factor. With mobility, having skills and experience being able to get from point A to point B being a major predictor of employment. It can also improve people's sense of self-efficacy and self-confidence, which also predicts employment. Of course, as we might expect, it impacts physical health. Getting out and walking, being physically active is a major predictor of various physical health outcomes. But it also impacts mental health. People who are active travelers have lower rates of anxiety and depression. And in the blind community in particular, rates of anxiety and depression are higher than in the general population. And finally, there's just the value of independence. So independence is an important thing to a lot of people. Being able to make decisions autonomously about where to go without asking for someone else's support is a major thing that a lot of people value deeply. So navigation is a major part of that. The underlying challenge, the thread behind all of this, is that there's a hidden demand for mobility. So blind people want to travel. They want to navigate independently, with 97% of blind people saying that if they had access to better navigation tools, then they would make more independent journeys. So the limiting factor here is not the people themselves. There are no inherent limitations on what blind people can do, on how effective travelers, blind and visually impaired people can be. The limiting factor is the relationship between the user and their environment. So a person without the use of sight faces challenges getting from point A to point B with navigating, because much of the world, our cities or homes, malls, airports, et cetera, are built for sighted people. So the assumption is that you can use your sight to read signs or look at paths or other objects far away, without much consideration for how blind and visually impaired people are supposed to get around. So the key is to bridge that gap. So technology has enormous potential for bridging the gap between users and the environment, in order to enable people to be as mobile as they want to be and to unlock that hidden demand. This image shows a picture of someone holding a white cane in their right hand. They're crossing a crosswalk and walking towards the viewer. White canes are an important tool used for navigation by blind and visually impaired people, with about 10% of blind people using white canes regularly. People will typically use them by sweeping them back and forth in front of the user's body, or by tapping it side to side in front of the user's body in sync with the person's gait, so with their pace of taking steps. And they're used to sense obstacles, so you can sweep it in front of you to make sure that there's nothing in your path, as well as to gauge the texture of, or what the ground in front of you is made out of, in order to figure out where you are and to gauge the terrain. So for example, the user can feel with the tip of the cane how hard the surface is to determine if it's grass or concrete, or they can listen to the sound it makes when tapping on the ground to figure out if it's sidewalk material or concrete or tile or whatever to figure out where they are. Guide dogs are also a really popular solution. About 2% of blind people own a guide dog. The main difficulty with both of these approaches to navigation are that with a guide dog, upkeep is an important and pretty time-consuming and expensive part. It's a pet. It's a living creature. You have to bathe it, feed it, take it outside, et cetera, care for it, and those all incur expenses as well. The white cane, while it's a very important tool, also has major limitations because its sensing radius is limited to its length. So the user can sense what's immediately in front of them, but nothing further beyond that. So if there's signs or visual information further in front of the user, the white cane isn't able to pick up on that information. So studies have found that while it does mitigate the risk of falls, so it doesn't do so completely. So blind people experience falls and collisions at a higher rate than the general population, and that's true even among people who use white canes. And the same statistics about how frequently people with vision impairments travel apply even when you're using the white cane. So even regular users of the white cane still don't travel as frequently as the general population. So we think that there's major room for improvement with this traditional or standard approach to navigation for blind and visually impaired people. We surveyed 100 people and conducted a handful of user interviews with about 20 blind and visually impaired people. We took a walk with a group of users, with a group of blind and visually impaired people from a community center. And we tried to distill what were the most challenging things about navigation to understand, what makes traveling so difficult. Some of the common themes were, there's a wide variety of challenges, but there are a handful of common themes. So one that sticks out is head level obstacles. This is one that a lot of previous technology solutions have attempted to tackle. And because the white cane is swept in front of you by your knees or feet, things that are hanging obstacles by your head aren't detected, so users can collide with them. Detecting objects of interest, so for example, doors, crosswalks, bus stops, other people, is hard to do with a white cane. Guide dogs fare slightly better, but aren't perfect. And that is an important part of navigation, getting kind of the last 40 feet of navigation. Once, for example, Google Maps says you've arrived, there's still the additional challenge of figuring out where is the door and how do I get into the building. Ground level features like curbs, steps, cracks in the sidewalk also pose challenges. White canes have some ability to deal with that and can kind of detect uneven pavement, but the white cane itself often will snag on cracks in the sidewalk, and people face challenges detecting them even when they have some training and use of a white cane. There's all sorts of different scenarios. So indoor areas, malls, airports, localizing where the user is, when they're walking with a white cane, finding a path, just, getting from, for example, your front door to the front door of a building, getting turn-by-turn instructions. There's a whole range of other problems that are difficult and that we think can be significantly improved. The past solutions, so I want to start talking about the work that has been done in this field previously. So electronic travel aids are any device that are used by blind and visually impaired people to make navigation easier. And there's kind of 4 areas that I think make sense to analyze electronic travel aids on. So the first is the form factor. So what the device does, or what the device feels like, looks like, what shape it is. So physically, is it a wristwatch? Is it something you wear? Is it a pair of glasses, or is it something you hold in your hand, etc. The second is the function, and the function of these devices. I think it makes most sense to talk about in terms of what information does this device relay to me. So going back to the kind of underlying problem. The difficulty is that visual information, which is available to sighted people, is not immediately available to people without the use of sight. So in what way and what types of information does this device extract from the environment in order to relay to the user? The third is the sensing technology. So what sensors does this device use to get information about the environment? And the fourth is the feedback method. So once the device has extracted some information about the environment, how does it tell the user about that information? And I want to go through a handful of examples of previous solutions. So this slide shows a table with the name of the sensor on the left and the kind of brief description on the right. And this is just the tip of the iceberg. There's been an enormous amount of research in this field, lots and lots of different devices, lots of academic research devices as well. So this is by no means a comprehensive list, but one of the first ones developed in like this, I think 1980s, it was called the MOAT sensor. And it's a handheld device that you point at something and it vibrates with frequency proportional to the distance. So it can give you distance information about obstacles near you, and it uses ultrasonic sensors to determine that distance. There's a device called the nav belt that the user wears just like a belt. It's fairly bulky and heavy and has a bunch of ultrasonic sensors, and it's meant to replace the white cane entirely rather than supplementing it. So the user wears it and they use this pattern of vibrations around their body to determine where obstacles are in order to try to understand the whole layout of their environment. The Ultra Cane is fairly recent. It uses an ultrasonic sensor to detect obstacles at the user's head. There's some other solutions that are kind of different from these like devices. So for example, there's an app called Pointer that uses indoor navigation using Bluetooth beacons. So there's beacons that the company places in malls or airports. And they use that to give directions to the user. Another app is called Good Maps. You use your smartphone to point around the environment to localize your location within a place that's already been mapped out beforehand. So it requires the legwork, for example, of figuring out like the blueprint of an airport and figuring out the layout of where everything is and so on. The Sunu Band is a wristband that uses an ultrasonic ranging sensor. And finally, the Envision Glass is a pair of glasses, actually very similar to the Google Glass, if anyone's familiar with that, that uses a camera and audio to give feedback to the user. So lots of different form factors. The set of sensors, a lot of them use ultrasonic sensors, lots of different feedback mechanisms. There's a great variety of different electronic travel aids that have been developed in the past. And the main thing the device we developed differs from these in several, I think, really important ways. So this slide shows two pictures of the device we developed. On the left is near the handle of the cane. So our device is built on top of a traditional white cane. So we start with the cane and we equip it with a bunch of sensors and a wheel at the tip of the cane to sense the environment and provide feedback to the user. So the picture on the left shows the sensors which are mounted near the handle of the cane. There's a white box containing all of the electronics mounted right underneath the handle, and a black, it's a LiDAR or light detection and ranging unit on top of that box. On the right side is a picture of the tip of the cane. There's a wheel mounted near the tip. The wheel is rested on the ground, and there's a motor connected to the wheel that allows the user that can steer the cane left or right. To kind of describe how this works, you can think of it almost like self-driving for the human body. So the idea is that the cane itself is navigating. It picks up information about the environment, and it uses a wheel to steer the user. So the wheel has these rollers around the edge of it. It's called an omni wheel, if anyone's familiar with those. They're really popular in the field of robotics. And the user can push the cane forward or backwards. It rolls on those rollers, and the wheel turns the user left or right. So for example, if you're walking towards an obstacle and the cane detects the obstacle, the wheel will turn the user, will start spinning to the right, and the cane will veer to the user's right. So it pulls you in a given direction, very similar to the way a guide dog would. The set of sensors includes a LiDAR, which I had mentioned previously. LiDARs are sensors that are very common in a lot of self-driving car applications. They were originally common in autonomous, in like flight applications as well for aerospace. But they're now available at incredibly cheap costs. So ours costed $100. And really that's the key to, I think, a lot of this technology that's being developed now. Prices for hardware are dropping rapidly. There's really lightweight algorithms that can be, that you can put on like small chips that, enable this technology to be available not just in airplanes and cars, but also on small devices that weigh just 2 or 3 pounds. And that's what we've managed to do in our case. This device, I think, we've achieved kind of a paradigm shift from the way previous electronic travel aids function. So a lot of them use ultrasonic or other sensors to detect obstacles in the user's environment and then relay that to the user just using vibration. We have shifted over to a device that actively navigates for the user. So the device itself is making decisions about where to go and how to get the user from where they are to their destination. And the user is following the device's lead. Empowered by many of the recent advances in autonomous navigation and other kind of AI disciplines. I want to dig into some of the key features that our device that I want to highlight for our device. So number one is that it maintains the familiarity of an existing white cane. So just like a white cane, it can be used to sweep it back and forth in front of you to detect obstacles. It can be used to shoreline, which is a technique where a person will follow a wall or the edge of a path or a road or something in order to traverse a room. And a major advantage of this is that if the battery fails or if there's some technology failure, it can just be used as a normal white cane, because at the end of the day, it's still a cane and it can be used as such. Whereas other devices, if the battery dies, it might leave you stranded, which was a major thing that we wanted to kind of prevent from happening. The device avoids obstacles, so it can detect obstacles as far as 10 meters away from the user and start steering the user around it. It can find paths, so it contains a GPS, and the GPS can map routes from your current location to a destination. It can recognize objects. So in addition to the LiDAR and GPS, there's also a camera, and the camera takes pictures of the user's environment and picks up points of interest. So some of those problems that I had mentioned earlier, like recognizing doors or crosswalks, bus stops, etc., the camera is equipped to deal with some of those tasks. And finally, the feedback method using the wheel, we think offers pretty significant advantages because it directly steers the user in a direction that they want to travel in, as opposed to audio feedback or vibrating feedback. And I'll dig into the feedback mechanism in more detail in just a sec. So we built our device about a year and a half ago. We tested our device in a variety of scenarios. So this picture shows a person holding the device is kind of out of view, but the person is blindfolded. There's a pathway constructed out of cardboard boxes. And this is inside of our lab. So there's these motion capture cameras all around the lab that can track the user's location. So as the user is walking through this pathway, we can track, at really fine detail how the person is traveling through the area. It's the same like motion capture used in, if you've ever seen like videos of like movies, it's essentially the same technology. So we got recruited 12 blind and visually impaired users from the Palo Alto Vista Center, which is a nonprofit institution for blind and visually impaired people. And we tested it by having people walk through these indoor mazes. There were a variety of different scenarios. We did a bunch of different mazes, different obstacle courses, walking through these cluttered indoor environments. We had people navigate outdoors as well, just a variety of different scenarios to test how our device compares to a traditional white cane. One of the other things we tested was also we wanted to compare our feedback mechanism to some of the other feedback mechanisms out there, which we had users hold the device and then try to turn to a specific angle, either left or right, within as fast as they could. And we compared how quickly users were able to get to that destination. So that turn in place experiment is the one I'll talk about first. So this graph shows the user's angle over time. So it shows the results of this turn in place experiment comparing 3 different feedback mechanisms. So the blue line is our mechanism, which we call grounded kinesthetic. That's our fancy term for the wheel. Vibrotactile feedback is just vibrating feedback, and audio feedback would be an audio instruction. So the vibrating feedback would vibrate more powerfully if the user got farther from this target angle, and it would stop vibrating once the user reached the heading angle that they were supposed to turn towards. And the audio feedback would just be like, turn 20 degrees to the right. So just a verbal instruction with no feedback beyond that. The graph shows the user's angle over time. So the user would be told to turn to face a specific direction, and the y-axis shows the difference between their current direction that they're facing and the target. So they start 50 degrees off of the target, and then as they receive feedback, they converge towards that target. And the x-axis is just how their behavior changes over time. So the audio feedback, you just get this one instruction, and the user starts turning pretty quickly, but remains 20 degrees off target by the end of the trial. And that's fairly to be expected. just hearing, for example, turn 20 degrees to the left, hard to figure out what exactly that means or where 20 degrees would be. Vibrating feedback, the user turns towards the target and slowly starts, continues turning towards it, ending up at a heading error of 10 degrees. So it takes more time for them to interpret what the vibrating feedback is trying to tell them. It takes more time for them to reach the target angle. And finally, this our method, this grounded kinesthetic feedback, users were able to reach the target much more quickly, with the users heading error decreasing rapidly and getting closer to the target angle than either of the other methods. And kind of taking a step back, what we think this kind of illustrates is that users were that our feedback mechanism imposes less cognitive load on the user. So rather than hearing an audio instruction or feeling this vibration and having to interpret, what does this mean? How do I respond to this? How do I fit this into the broader context of where I'm going? The wheel immediately just pulls them in the direction that they're supposed to face it. So there's no sort of intermediate cognitive task that has to be accomplished between the instruction and the user responding to it. It just does it for them. And that's important because navigation is a taxing thing to do. Getting from point A to point B, especially when you don't have this use of sight, you have to listen to things in your environment, try to understand where you are, listen for people, traffic, other stimuli in your environment, and it's difficult. It's cognitively taxing. So a feedback mechanism that imposes as little cognitive load as possible on the user is a crucially important part of our system, and we think is a massive advantage of our system over many of the alternatives, over most of which use audio or vibrating feedback. The second set of experiments we did were these obstacle courses, which I had mentioned previously. And this image shows the paths taken by one person through this obstacle course. So the blue line is the one taken when using Arcane, and the orange line is the one taken while using the standard cane. And what the graph shows is that the person starts walking. Halfway through the path, they kind of turn all the way around and make really sharp course corrections as they encounter obstacles along the way. The path taken by people using our device is much smoother because the device is able to anticipate where obstacles are before the user touches them with their right cane. Because they don't have the use of sight, they can't anticipate it themselves. So that's a major advantage of our system. On the whole, we found that our device is able to reduce the amount of time it takes for people to get to their destination, reduces the number of contacts people make with their environment, and allows people to actually walk faster. So this is another element of cognitive load where many of the previous devices in the past have actually slowed users down and reduced their walking speed. And instead, we were able to increase users' walking speed, which we think is important. It makes navigation a lot easier. And it also comes with, we measured a person's kind of metabolic cost of transport. So literally how much energy do they expend while getting from point A to point B? And we were able to reduce that metric as well. And what we think this shows is that people were much more confident. Literally, they're more sure-footed when navigating. And I think walking speed is an especially significant element of that. Being able to just walk without being too concerned about where the obstacles are and letting the cane kind of guide you along this path is a major feature of our system. This next graph shows people navigating outdoors, and basically similar theme here. So they were using GPS in this context, and each little dot is one GPS measurement. And again, the idea is that people deviate from the route much more significantly and make sharp course corrections when using the standard white cane with audio GPS instructions compared to when navigating with our system. And again, we were able to show that it improves users' walking speed, gets them to their destination in less time, with fewer collisions with obstacles, and so on. So the major metric, the major takeaway here is that people get that navigation is easier. If you can get to your destination in less time, without making as many collisions with things in your environment, the whole task of navigation has become substantially easier. Another important feature of our system is what we call visual servoing. So one of the things I mentioned earlier was using the camera to take pictures of things in the environment and navigating to them if the user is interested in interacting with them. So for example, doors to a building, kind of in the last 40 feet of navigation, figuring out where bus stops are, where crosswalks are. All these are important tasks that people who are blind or visually impaired often find challenging. So we use this technique called visual servoing. We take a picture of what's in front of the user and recognize a key object in the frame of the image. So in this case, we just used a stop sign as kind of as an example. So the user is facing a stop sign, the camera takes a picture, and you see the stop sign in the frame, and you use the location of the stop sign within the frame to steer towards it. So for example, if the stop sign is left of center, then we know that the user is to the right of the stop sign, and we can steer the user to the left to get to the stop sign. So this graph shows 3 routes taken by users at different starting points. So one is facing the stop sign directly, one is off center from the stop sign, and one is even further off center from the stop sign. And what we're able to show is that users our system can effectively navigate people to this stop sign, to this destination, just using the camera, with the goal of kind of keeping the object in the center of frame to make sure that the user is walking right towards it. And this was also measured using that motion capture system that I had mentioned previously. The last thing that is kind of an interesting feature is what we call simultaneous localization and mapping. So this is a technique that I think has gotten a lot of attention recently in the domain of robotics and autonomous navigation. We use the LiDAR to pick up a set of obstacles in the environment. And over time, we stitch together multiple measurements to figure out where obstacles are. So it's a technique that both figures out where the user is and where obstacles are relative to the user. We had people navigate in this cluttered indoor environment. So there's all sorts of stuff like a desk, table, drawers, chair. This image shows a bird's eye view of the user's position over time and all of the other stuff in the environment. And the idea is that we wanted to measure is, does our system effectively get the user, does it estimate the user's position in the environment close to where the user actually is? So we get the ground truth using that motion capture system that I mentioned before. And the system is trying to figure out where the user is in relation to all of these obstacles using measurements from the LiDAR. So mapping out the environment and figuring out where the user is within it. And it shows that obviously there's some significant error, especially as the user moves. It's somewhat jumpy figuring out where the user is in relation to where they actually are. But on the whole, we're accurately estimating where the person is, in relation to their environment. So in indoor areas, for example, malls, airports, et cetera, this is like an important task to figure out what your environment looks like and getting the user to navigate through it. Taking a step back and kind of thinking back to that context. So, people are using our device. Their goal is to get from, their home to some point of interest. So bringing in these 3 different, modes. So navigating indoors through these like indoor maze type things using simultaneous localization and mapping, navigating outdoors using GPS, avoiding obstacles, and finally using visual servoing. We constructed an example use case of the device. So we had someone start indoors. Their goal was to navigate from this indoor location to get out. Then they would use GPS to go from one location outdoors to somewhere else. And then for the last 40 feet of navigation, they would use this visual servoing algorithm to get them to some point of interest. So in this case, again, we just use the stop sign as an example point of interest, but a real use case would be something like a bus stop or the doors to a building or something like that. So the map, this image shows a map. It's again a bird's eye view of the route a user took. And the idea is that, while they're indoors, they're doing this obstacle avoidance technique to just avoid things in the user's immediate vicinity. As soon as the user goes outdoors and the device is able to establish a GPS signal, it switches over to using a GPS-based navigation method. Along the way of GPS navigation, there's an obstacle that the user encounters. So there's, I think in this case, there was like a pothole with construction signs over it. So when it detected the obstacle, it reroutes them around the obstacle and then continues navigating with GPS. And finally, the whole time it's taking pictures and trying to see if it can recognize this object of interest. So once it does, once they're within sight of the stop sign, it takes them that last 40 feet, towards the stop sign and gets them to their destination. So you can imagine this in a variety of contexts where a person is trying to navigate, and our system is able to address that case. So they're indoors, they're trying to get to like the grocery store or whatever, they first have to leave their apartment building, navigate with GPS for a little while, and then navigate to the door of the grocery building or whatever. And that's kind of the idea that we're trying to demonstrate that our device is capable of achieving. There are three major pieces of feedback that we want to iterate on. So number one is the weight. So our device is a lot lighter than a lot of the competing projects out there. So, for example, there's devices that weigh up to 10 or 20 pounds. Ours weighs 3 pounds, but it's still heavy enough where if you're using it for an hour, it starts to become burdensome. So we want to greatly reduce the weight in our next version. We want to make it more ergonomic, so making it easier to hold, especially making it easier to hold upright, I think is an important target for additional development. And finally, making it very robust to all the edge cases that a person might encounter while navigating. Obviously, this is something that people would use in a variety of different contexts. The real world is scary. There's lots of stuff, traffic, other people, et cetera. And we want to make sure that our device is safe and can adequately deal with all of the different cases that come up when someone is using this in a real world context. I want to close by talking about briefly the future of devices like this. There's a textbook from 1986 about orientation and mobility that had this quote that I really liked. And the quote says, "With continued development, electronic travel aid devices should become smaller, more reliable, and easier to use. They represent a leap forward in independent travel." And I think with the recent developments in this field, so like I said at the start, reducing costs for sensors, hardware, new algorithms that are more compact and lightweight, better batteries, all of the developments in the technology have gotten us to a point where I think we're finally ready to make that leap forward. Devices are becoming super compact, super lightweight, and I think that there's an enormous opportunity in the next few years to see these devices become very widely adopted and extremely usable, and really unlock that hidden demand for mobility. Questions?
Hey, Arjun, that was great. So what I want to do is there was a couple questions, and there was a couple that I think that was more appropriate that like open it up to you and Neil and Patty and Mike. But I had a couple that I just wanted to see if you could knock out real quick. One thing that I was interested in is you had like the object detection, and I was just wondering, can you talk any about like the tech stack, like some of the are you using certain software libraries or machine learning libraries or object detection libraries, like a little bit about those technical details?
Yeah, that's a great question. So I think what was really cool about this project is that we didn't have to build very much from scratch. So really, it was a matter of taking these components that other people had built that were publicly available, and stitching them together to build this comprehensive kind of end-to-end system. So, for example, the lidar we built, the lidar we got, it's its own package. It's $100. There's SLAM, so the simultaneous localization and mapping software is an open source package called Breezy Slam, developed by someone else. The computer vision algorithms it's this pretty popular framework for object recognition called You Only Look Once, or YOLO. And there's even a version that's equipped for really small form factors or limited compute without like a GPU or anything, called I think YOLO Tiny or Tiny YOLO. So it was really a matter of finding the right packages or the right libraries for all of this, and there was very little like custom development that we had to do. We didn't have to write, for example, like SLAM or train any convolutional neural networks or anything from scratch, which I think is really helpful. And that's the development in those previous areas is what made this project possible for sure.
Cool. So at this point, I'm gonna change it so everyone can unmute themselves. So definitely Patty, Michael and Neil. And then there was a couple questions that I'm going to ask, but the folks that asked the question, if you guys want to clarify after I ask the question, you can unmute yourself now. One of the first questions was kind of like the form factor and how you have this set up as a smart cane, but it felt more like it could be a robotic guide dog. And did you have any thoughts on, would that be something better? And then could they actually have a robotic dog with a traditional cane? And then I'm kind of add on to that. Is there anyone doing that? Is there anyone kind of looking at building like a robotic sight dog?
Yeah, that's a great question. And I think it's from Hobson. So hey, yeah, I think it's really interesting. I think the main difficulty is that like a dog is just if you've seen those like Boston Dynamics dogs, like it's like very technically difficult to pull off. So and I don't think there's a ton of open source stuff in this domain. So I know my co-author Patrick Slade, who's that postdoc who focuses on assistive technology, built and released a library for an autonomous dog. They called it the Stanford Doggo. But it's I think at the end of the day, like you want something that still has the form factor of a cane because it can be used like a cane to detect obstacles through just the sense of touch. And that's why we picked that form factor over something else. And of course, there's just like the technically difficult challenge of like getting this like four-legged creature to walk and getting it to walk upstairs and terrain and all of that. And it seems much easier to deal with that by just having something that's super lightweight. The user can just, pick it up or even fold it up, in like indoor environments and stuff like that.
Every attempt at either dogs or guide robots or dog guide robots, whatever you want to call them, has ended up in the millions of dollars. It's extremely difficult. That's why I've been interested in this project, because it makes as few changes as necessary without changing what the user fundamentally is doing. The other thing I would mention, just because I know most people don't use canes, obviously, or dogs, either one. I'm blind, by the way, and have been a travel instructor since the 1980s for blind people. That most blind people who travel with a dog, if they're going to an unfamiliar area, carry a cane. And the reason is because the dog will stop at a corner, at a step, but you don't know what it's stopping at because dogs can't communicate with you. So most people carry a cane. That's why the cane has always been sort of in the modern era since the 1930s and 40s, the primary tool that blind people use to travel with, because it's so much of an analog tool that you can detect information with it, et cetera.
Actually, that I kind of wanted Neil, Michael, and Patty, do you guys want to do like a quick sentence, just introducing yourselves, because we didn't get a chance to do that.
Go ahead, Neil.
Sure. Okay. So hi, I'm Neil Rothman. I'm a professor of biomedical engineering at Stevenson University. My background's in medical device development. Also volunteer with the Image Center of Maryland, developing solutions for people with disabilities.
So I'll go next. I'm Patty Della Fuente. I am a data scientist and solution architect for NVIDIA. I also teach an applied AI course at UMBC for the graduate data science program. And I don't really work in the space. I tend to work more in AI and robotics, but I was approached by Neil and Michael over the summer about how we could leverage AI to support the blind. And so that kind of got this whole thing going. And I've been fascinated ever since, because it isn't a discussion I've had. And if you were to ask me right up front, I probably would have said, let's build a dog. And talking to Michael has like opened my eyes up significantly, to the point where I'm like, we need to get the community to hear what he has to say, look at what's out there. And then really it's, I work for NVIDIA, so we have all of this amazing technology. But the application of it really involves partnering closely with the community that's going to use it, and it has that domain expertise. So I'm so glad you guys are here, and I really would love Michael to really give you more information about how why a robotic dog wouldn't work for him, or a robotic person, so that you guys could understand what I've been made to understand. It's just kind of opened up a whole new perspective for me. But thank you, Jason, for setting this up.
Yeah, and I'm Mike Bullis. I'm executive director of the Image Center of Maryland. We're the organization. We build technology devices for people with all kinds of disabilities. This has been one of those projects on my list. In fact, I wrote an article that almost described Arjun's almost described Arjun's device, only he did me a couple of one-betters in the way he developed it. I found him online and said, hey, let's talk about this, because they're really, most of the projects, and as you can imagine, being involved with blindness and with disability, I get people who come to me all the time who have the newest, coolest, greatest device that's going to solve so many problems. Unfortunately, they usually don't know any people with disabilities. They've never tested it with people with disabilities. And so they don't even, they don't usually begin with that thing that they would use for most other devices, which is, let's go see what the people in the market actually need. So dogs are incredible, by the way. One of the nice things about dogs is you can point at somebody and say follow, and the dog will follow. You can't do that with a cane. You can go faster in a crowded area because dogs can weave around people, whereas with a cane you have to contact the person's legs or something. I gotten hit a couple of times for that, but you have to contact the person in some way in order to go around them. So crowds can be difficult. Looking for an elevator, an escalator with a dog that you keep in good training. And that's the thing about dogs, by the way, you have to constantly reinforce what they were taught when at the schools. If you don't use them every day and don't keep them in tip-top shape, they start forgetting, and pretty soon they're just your dog. But one of the cool things about dogs, you can say, hey, find the stairs, and the dog will look for stairs and take you there. So most blind people would say to you that they love the idea of a dog. They just aren't dog people. They don't want to do the care. They don't want to go into work in the morning with a soaking wet dog that they then have to deal with, and then they have to take the dog out 3 or 4 times a day. Dogs are a process, and a lot of people just aren't dog people.
Thank you for the intro. So there was another question about this was a little bit of a longer one, but basically it was talking about when you were focused on the way that the cane was pulling people, like kind of directing the user. The question was, would it make more sense to actually do a zigzag pattern that you would be more likely to detect any obstacles in the way instead of a direct? And I was just curious what you thought about that, Arjun, and then Michael and others. It was an interesting question. There's more text, and the person who asked the question, if you're still on, you're welcome to unmute yourself and add some more detail if you like.
Yeah, to answer it, that's actually exactly what it does. We were thinking the exact same thing, and we wanted to replicate the function of a white cane as much as possible. So when it's navigating, it is sweeping back and forth. So especially in the absence of an obstacle, it's kind of constantly sweeping. And when it encounters something, it continues sweeping. It just it kind of sweeps away from that obstacle. So totally agree, and that's exactly the idea. So it's kind of this zigzag pattern. And one thing to clarify is that it's only pulling left or right. It doesn't pull the user forward. So there's just a single wheel, and the wheel turns left or right, and it has those rollers around its circumference that allow the user to push it forward or even backwards if need be, because we don't want to try to control the user's walking speed or pull them into something.
You guys are welcome to jump in. I'm going to continue to ask questions that interest me if no one's going to jump in. So there was a question, and it's kind of what I was thinking. I mean, obviously, I'm not blind, but the one thing that I'm thinking about, and this was asked, is the greatest fear would be stepping out into traffic. And is that something where you would put your trust into one of these smart canes? Would that actually prevent that, I guess?
Yeah, thanks. I saw that question. It's a great question. One of the things we spend a great deal of time in teaching blind people, new travelers, is how do you detect information at an intersection? How do you know where the traffic is going? Blind people have been crossing 5, 6, and 7-way intersections for 40 or 50 years. It's not a problem if you got somebody who can teach you how to use the information. My hope is that with devices like this, perhaps we're going to be able to, through some fairly sophisticated analysis by the AI, be able to give the user information about the intersection. This is a 5-way intersection. You're facing here or there. In other words, I think complex street crossings, not your regular 4-way intersections, by the way. you're going to have to be able to hear and not step out in the street and so forth. I don't know that there's what dogs do with that information, by the way, and maybe we could incorporate that into this device, is if I walk up to a corner with my dog and I then step out into the street as though I'm going to cross and there's a car coming, the dog simply refuses to go. The dog just stops and won't go. That it can't tell me when to cross. It can't tell me where the 5-way intersection is. It can't give me any of that information. But if it detects a car coming at it, the dog just steps back and says, no, we're not going anywhere. So that's a good question. And it's a complex answer that I'm not sure we fully are going to be able to solve.
So let me just interject one thing as well is in thinking about how to come up with kind of just solutions in general for people with disabilities, a lot of times we try to provide a complete 360-degree solution, right, that does all of these great things. And it turns out that that's not what the user needs. I think what Mike's sort of alluding to is we need to replace the fact that they can't make continuous observations and decisions about the things that are around them because they can't see them, but they can still hear, they can still smell, right? They can still have all of these other inputs. So don't worry about those, right? Worry about the things that they can't do because they can't see, and try to figure out how to provide that navigational capability that we do completely unconsciously to help them then integrate that with all the things that they can sense. And I think it's a real challenge a lot of times, because as engineers, we want to make this great solution that can do all of these wonderful things. And it turns out a lot of times it's really overkill. And I think Arjun said it too. It's too much information. It's too much of a cognitive load for the user. You want to make it as transparent as possible, and just help them do the things that they can't do.
Yeah, I fully agree with all of that. I don't think I have anything else to add there.
So I had a question about it's kind of going into the business side of this. So like I don't know, I'm not an academic like you, Arjun. I'm not doing these kind of things, but what I'm trying to understand is there a market for this? Like it always seems like things like this, to be like mass adoption or to get like a commercial entity to produce it, there's going to have to be a market, right? A value. And are you seeing that? Like, do you envision there are companies standing up to actually build these kind of products, or maybe there are already companies like this I'm not aware of?
Yeah, great question. There are a couple companies in this space. So for example, there's a cane called WeWalk that it's a startup that was launched a couple years ago. I think it just uses an ultrasonic sensor to detect obstacles at head level, and then provides like vibrating feedbacks to help the user follow GPS instructions. There's a handful, and a lot of those devices in that side of examples of previous work. A lot of those are commercially available devices. We think that what we built can improve on some of the existing things out there already, and we are exploring options for getting this out there. Because we think it should be in people's hands. We think that it's a really powerful technology, so we're actively looking at ways to help commercialize what we've built.
I think one of the primary thoughts, as if these kinds of technologies, as in the rest of the technology field, if these kinds of technologies actually work, the vocational rehabilitation field, the field that trains blind people and helps them get employed, is going to want to pick this up. And so that's one area that provides you several tens of thousands of customers. Certainly there are organizations of blind people around the country and organizations that serve blind people who, if this device can really make a difference, are going to want to do it. The thing that stops some of these devices is that they simply are too expensive, and that the average blind person simply can't afford them. You're not going to get this down to $10. It'd be nice if we could, but right now a good cane costs 40. So I don't think we're going to get this under that. But I think if you can't get it under a few $100s, then the average adult blind person who wants to buy it is simply not going to be able to afford it.
So do you guys, this is kind of for Neil and you, I guess, Mike, do you guys find did these companies come to you like in the with the image center? Did they come to you with these ideas? Like, do you have relationships with these businesses that are producing these?
Not with WeWalk. I have certainly worked with several of the, so there's lots of technology around computers, for example, to make them talk, to give braille displays for blind people. We work with several of those companies on a regular basis, the American Printing House for the Blind. In other words, yeah, there are some companies out there that are interested in us and in what we do, and in hopes, I think, that they'll sell something along the way.
Yeah, I would say that when we're trying to find a solution for somebody, one of the first things we do is say, is there a commercial solution? And right, is there something that we can just buy for them or help them buy or those kind of things? It's in the cases where those things don't exist that we would then look at develop something that's custom. And I think this is, this kind of technology is something that I think would be, much more, isn't sort of a one-off for one person, right? This is something that could have much broader applicability.
If anyone in the audience has questions, just go ahead and ping me or unmute yourself. So this one's kind of for Patty. With the advances in edge AI and continue like AI products, like some of the stuff that you're seeing, do you see that there's opportunities to continue to improve the works that we're doing in the disabled community? I kind of butchered that question, but I think you know what I meant.
Yeah, there's so many amazing things going on. And just to piggyback quite off the last question though, many of the prominent companies like NVIDIA do have what's called Inception programs. So if any of you on this meetup has a startup or you have an idea and you're interested in leveraging that, you can apply for the Inception program, and that gives you, it can connect you to funding sources. A lot of times we'll donate hardware. You can apply for a hardware grant, and also there's a lot of training you could get for free and stuff. So there's a lot of options like that. But in the whole AI ecosystem, there's so many advances now, like even just within NVIDIA itself, we have a lot of probably at least over 100 permutations of pre-trained AI models, anything from detect net object detection. We have all of the sample source code and containers. A lot of the containers are free that you can download if you have the hardware that supports it. Things like traffic cam net, all of these things. So you don't need to start from scratch, because starting from scratch would make it really expensive, but you could start from a position of having a pre-trained model that can already recognize street signs, vehicles, people, and other objects. And that's a framework that you could start from to build your solution. The other thing is we also have done so much in the space of, it is when you're dealing with AI, that there's the edge piece where the cane that you have to talk about, you have to do some inferencing with, with your neural encoders and things like, depending on what you're sensing. So at the edge, hardware has gotten smaller and more efficient, where we can add, have GPUs in very small form factors. When you can offload that to a GPU, it's more power efficient as opposed to trying to do it on a CPU. So we're doing those kind of things, and that's in my class. I actually teach the students using the Jetson Nano 2 GB so that we can teach how to do things at the edge. It also makes it really affordable for our students. They don't have to go out and buy a high-end GPU to learn how to program on GPUs and use some of the AI models. But then also, we handle, we have the high-end ecosystem of servers and clusters and compute clusters. We're in the process of building one of the fastest supercomputers in the world. But so we have the compute power that you also need to build these models. So we are so anyway, and there's so much work being done in that manner. There are other things that besides for the other disability community, there's a lot of work being done for the amputees. We've got there's some amazing groundbreaking work they call it path breaking, where they've actually had neuroscientists identify the neural pathways and they have and they use these GPU powered devices for the inferencing and besides for the training, so that you can have amputees think of something like, or control something, and that translates, they can take those sensors and translate that into movement with the prosthetic limbs. So there's so many things, like, whatever you think of, if you have an idea, if you're working with somebody who has that domain expertise, just reach out to the community. And so then that's my goal, is I know of all of this technology. I would love to work with folks that have the domain expertise and drive you in the right direction. Because like I said, if I were to just invent something, I love robots. I would think of any excuse to build a robot, but that's not going to help Michael out. So understanding that what Michael needs is just a way to replicate what he can't do. That CNI dog provides a specific functionality to see and detect a moving car. So that's what he's trying to solve, is how would you replicate those commands, but then translate it to a cane or something like that. So it's just, my motive here is just to really pair the community. For my side, I can show you what technology is available. For Michael's side, he can show you what they need, and that's the case for any type of object like this. So, any other questions?
That was really helpful. I'm sure there's a lot of opportunity. Actually, I had a question, because so much of this is so dependent on hardware, right? Building the cane and stuff. Is there work that folks can do to kind of get involved that are just focused on the software side, like coming up with new models, or doing, like, just is there data sets that are available? I don't know how you would really get the data set, but I'm just wondering.
Yes. So you can actually get involved in the AI community without touching any hardware at all. Right now, there's a lot of advancements being moved to enable things to be done in the cloud. So there's been a lot of work across all the major vendors, and NVIDIA included. And NVIDIA, we're usually under the covers. You don't know that we're there, but we're there. Like, we're there under the covers for some of the compute things you see with Amazon and Microsoft and Facebook. But you can. Most of these vendors offer ways that you can learn how to train a data set. So it just depends on what your goal is. If you're learning, and there's also, Omniverse and Metaverse. So there's this whole drive to do digital simulations. So, and the motive behind a lot of what we do at NVIDIA for increasing compute power is just to do that. To do these large scale simulations requires significant compute power. So we even, in class over the next couple of weeks in class, I'll be covering how to navigate, obstacle ramps and navigation using our little Jetson devices, but also to do it for those who don't have like JetBots, like what I have in back of me here. We can do it virtually using a simulated environment. So, and so that's something that users could also look into if you don't have access to, if you don't want to send somebody out to navigate New York or something like that, you could look for a digital version of that and train your data set that way. Sometimes getting access to the data is hard, but if you could generate, if you have a simulated environment, you can generate data that way. So there's just a lot of different options. I just feel free to reach out to me. I'm on LinkedIn, and I'm happy to try to help or connect you to other folks who might know something more about like the different area that you're looking into.
I love to travel. I travel regularly throughout Baltimore and other cities. And the other day I was out traveling, and I have 3 devices on my phone live at all times. I have Google Maps, because it's going to tell me when my next turn is. I have Microsoft AI, because it describes features that are around me, like it will say crosswalk. Now, it won't tell me where the crosswalk is exactly, but at least I know there is one. And then I have a thing called Blind Square, and its unique feature is that anytime I shake it, it will make its best guess at what address I'm at. And so, we're getting there. Now, it does take me, like I say, I have to load all 3 of these programs all the time on my iPhone in order to get that information. But usually they don't fight with each other too much. And I think the important thing is I'm still having to make all the primary decisions about where I'm going to go and when I'm really going to turn and whether I think I'm really at that crosswalk, et cetera. So the more we can give, especially older blind folks, blindness, less than 10% of blind people are blinded before the age of 18. The other 90% are blind as adults and lose their vision as older folks. So the more confidence we can give these folks that they're not simply relying on themselves, that there is more information out there that they can get, that there are devices out there that can help them, the more we can get people out and moving and functioning. So it's a work in progress. All of this is, I think this device is going to make some real progress in that direction. And then, and then there will be others that come along afterward. I think this is the beginning. Our basic rule is don't do what you already can do. In other words, I don't need a device that can walk up and down stairs. I know how to do that. I don't need a device that can well, I think that's the classic example. That's the classic difficulty that the robot folks make, is that they keep wanting to have a guide robot for me. The logic is, hey, blind people's best form of travel is to just take the arm of somebody and go somewhere. And if we just make a robot for the blind person, then that would be fine. The problem is 10 or 15 or 20 millions and millions of dollars later, we still can't get robots that can really always identify stairs and go up and down them and identify terrain, changing patterns, et cetera. And besides that, I can get up and down the stairs already. So we're solving a problem that we didn't even have.
Yeah, I'll come back. I think, Jason, you had maybe made a point earlier. I just wanted to kind of expand on it a little bit, is that if we think about this particular problem, there's really two pieces of it, right? One piece is sort of the physical implementation. How do you provide that feedback and direction for the user? And the other piece really is I'll call it the technology side, right? How do you take in the environment and provide the information that could help guide the person? And I think both of those are really, really interesting areas to work. I think most of the folks here are, and I know Patty is for sure, right, are very interested in that technology side, right? How do I take sensors, how do I take LiDAR, whatever it is, and be able to capture the environment and extract enough information out of it that I can use that to help that person navigate, right, and avoid collision with things and those kind of things. But then the physical implementation is, okay, well, it's not a dog. A cane seems to be something that's pretty logical, and the rolling wheel is pretty simple, right? Is that the best implementation? I don't know. It seems pretty good, right? But so I think there's kind of, right, I think of the problem kind of in two pieces, because if we can do much, much better in terms of right, I'll say characterizing the environment and figuring out what paths should be and what the information is that we can provide to help guide the person, then we can also work on how do we guide the person, right? And I think those are two just really interesting questions to be able to really solve this problem.
So Arjun, I had a question related to the data aspect. Does your device actually collect data as it's going, and do you do analysis after the fact and trying to improve it based on the data you collect?
No, not in its current form. I think that's something we want to explore. The major kind of issue to think about there is privacy, just because the device could be a lot of the time in inside of the user's home or their apartment building or whatever, where there's potentially sensitive stuff going on. The other thing is, the device has to be pretty small, which means the onboard, whether it's a microcontroller or microprocessor or whatever, has to be pretty small too. So there's constraints with respect to memory. And of course, it could be something that we add, for example, make it interface with the user's phone via an app or something with Bluetooth and upload data rather than trying to store it locally and save it at a later time. There's ways around many of those constraints, but those are kind of the two things to be cognizant of as we do that. But I think absolutely long term, that's of interest. I think it's important because you want the device to get better over time. I live in San Francisco. There's these like Waymo cars, the autonomous, cars from the Google X spinoff. And, that's exactly the point. Like they're always roaming around, they're collecting a bunch of data. And that's an incredibly important aspect of developing a system that's able to, truly make autonomous decisions and do so safely. I think so long term.
I can't wait for that.
Absolutely. Yeah.
I want that self-driving car now. I'm telling
They
you.
actually just started fully autonomous driving, I think this like yesterday or last couple days. So pretty
Very
cool.
exciting stuff.
San Francisco, but yeah.
There actually was a comment by Levin, I believe, and it was talking about adding some concept or something that would actually summarize the current scene that the user is in the user's view. But it sounded like what Michael was running with the Microsoft AI, which I'm not familiar with, does that. Is that right?
Oh, it does a little. It's kind of experimental, and really, like I say, the most interesting thing is it identifies sort of. I don't know where it gets its data sets. It'll tell you that there's a university, and what that really means is you're within several blocks of a university. So it's really tends to be a work in progress that I find sometimes useful and sometimes not. But that's true of all the data sets. There's the other one that I use, this blind square, and it will tell me, it will make its best guess at addresses, but it's not very accurate. It's within like, a couple hundred feet, but hey, I'll take a couple hundred feet as opposed to, nothing. And then I can either stop and ask somebody or check out local features that I'm familiar with if I've ever been to that place before and go, oh yeah, I see, we're at the house next door, right? So, the more information you can get, the better. Google Maps has walking directions that are pretty good most of the time, but sometimes it just doesn't quite, it'll say the corner's in 75 feet and really the corner's in 175 feet. So I have to just use my intelligence as I go along, say, well, okay, which is, by the way, my scary thought about some of the self-driving car information is that there's the information that we have that still really needs to be much more granular than it actually is so far.
So are all those apps talking to you at the same time?
So they don't interrupt each other that much. I can set them so that they, the Microsoft AI, for example, will say approaching intersection. Well, that's good information. And it's, for some reason, somebody loaded it with a map of all the alleys. Now, if you've ever been in Baltimore or East Coast cities, every street has an alley. And so you like to know that stuff. And so it'll say, alley on right, alley on left, road, such and such name straight ahead. And so now you just said, oh, okay, so this isn't a corner. This is just an alley that I'm passing. Well, Google Maps doesn't talk about any of that stuff. It doesn't tell you where the alleys are particularly. So it's a matter of sort of piecing together information as you go.
Oh, that's interesting. So we got a couple minutes left, and then I was going to start wrapping it up. Is there any other questions for the group? Anybody from the audience? You can type it or speak it, whatever you feel more comfortable with. All right. Well, I give people an opportunity for the last question. So
hopefully when your aunt or your grandmother, if they start losing their vision, hopefully what we're going to be able to provide for them is the security of saying, I used to walk around in my neighborhood. I'm afraid now that if I go out, I'll be running into things. And hopefully what we'll be able to do is give them a device that they can trust that will guide them around the tricycle that the neighbor left out in the sidewalk, right? Or the garbage cans that are sitting out from last night, et cetera, so that they can go once again to have some kind of freedom of travel that most older people, when they lose vision, they start losing that freedom of travel.
So Arjun, are you still, maybe you answered this and I missed it. Are you still working on this? Is there other people in your, at your school that still works on this? Are you guys continuing to build?
Yeah, we're definitely, still iterating on it, actively trying to build a second version that addresses some of the shortcomings of the first one. So absolutely interested in continuing development. And like I said, also kind of with an eye on not just like producing another paper or whatever, but getting this in people's hands in whatever way I think is most appropriate. Because ultimately we want to have an impact. We want to get this device out there and have people using it. So figuring out, how to do that and also how to build something that people will really love is the main focus. I did want to add in response to Levin's question of like scene summarization. Definitely, I think like pretty interesting. As far as I know, Seeing AI with like the Microsoft app that Michael was talking about doesn't do like full scene summarization. So it picks out some ththings, but if you like, point at like a park or whatever, then it doesn't give like a full, description. So I think that's super interesting. To my knowledge, I think there are some teams working on it. I think Seeing AI themselves are working on it as well. If I remember correctly, I think they gave a talk at Site Tech Global a few months ago. And but yeah, I think it's a super interesting field. I think in the context of our device, it makes sense to kind of focus on a few things at a time. So focusing on like navigation and just really nailing down the problem of like what is hard about navigation and tackling that rather than as both Michael and Neil alluded to, trying to do everything. But absolutely, I think it's an important and like really powerful idea. And it's really cool that like a lot of research is being done in that space now. So I think, thank you for that suggestion. And I think it's a really cool application for sure.
By the way, I've been giving you guys bad information. The product that Microsoft is developing is called Soundscape. That's the one I've been using, not Seeing AI. Seeing AI has its own possibilities, but Soundscape is the one that they're playing around with. So sorry about that.
That's like the audio AR type thing, right? It's like the sounds like they try to make the sound come from
where the object is. Yeah.
Right. Gotcha.
Yeah. It'll say, intersection on or alley on left, and it comes out of your left earbud. So you
right.
Oh, okay, got it.
Yeah, I think that's super neat. And that same, I think that it was that same talk from Site Tech Global, the developer. I don't know if he's associated with Seeing AI or Soundscape, but he was talking about that. His name is Saqib Sheikh, and it's a cool project. I think it's definitely very impactful. People really do like it. So
yeah.
I'll just add one quick thing about scene summarization. So there is definitely a lot of work in that area, and especially because that's needed for things like robotics, but also self-driving cars. And like, so at NVIDIA, we have a product called Drive. We have Metropolis. So we definitely have lots of pre-trained models to identify different objects. And we have, like there's sample code, if anybody needs it, just ask me, where you can integrate multi-networks. And because that's a lot of times that's what you're doing is you start with one object detection model and then you need to layer something on top of it. If you need to identify a car, then maybe you need to identify a license plate. So there's many of these for these scene summarization areas. It's just a matter of putting many models together, and then really once you have the inferencing, once you have the object detection that you need and in the output and the format that you need it, then you have to really fine tune that model and streamline it and remove all of the noise so that you can get it to a point that it's as small and lean as possible to optimize your inferencing. So there's a lot of work being done in that. I don't know exactly how I would apply that to Michael's scenario, but I'm just letting you know, just sharing that info with you.
Great. Okay. Well, I think I'm going to wrap it up. I mean, that was very interesting. Thank you, Arjun, for the presentation. You're doing some pretty awesome stuff there. And I never realized how much is going on. Like the Microsoft research, that was very interesting to look at. So thank you, Patty, Neil, Michael, Arjun. Thank you, everyone, for joining us.
Thank you all.
I would say that if anyone in the audience was a little hesitant to speak and you want to learn more, definitely reach out to the Image Center with Michael and Neil, or reach out to Arjun, or reach out to Patty. I think everyone's pretty accessible. And if you need the information, you can reach out to me and I can put you in touch with them. But thank you, everyone, for joining. Thanks to the panelists. And I hope everyone has a good evening.
Thank you.
Good night. Thanks, guys.
Thank
Bye.
you.